Okay, so vectors and scalars in real space, particularly vectors and scalar fields in real space, have another interesting property. We can not only evaluate them at a point and do all of the algebra we might want to, adding them together, dot producting them together, cross producting them together, that's all kind of point-wise stuff, but we can also compare them to their value at a neighboring point. That is, we can take their derivative in space. We can take their derivative in the x direction using the x partial derivative. We can take their derivative in the y direction, their z direction, or their derivative in time, because we normally think of a field as being expressed, let's just start with the scalar field, as being a function of x and y and z. So it is at a position which has a different dependence on each of the coordinates, and potentially time. Cool. All right, so if we take the time derivative of this, then we just need to think about how s varies in time. If we take the x derivative, we just think about how x varies in the x direction, y derivative, y direction, and so on. That's great. That's not too hard. We can do the exact same thing for the vector, and the vector might also depend on x, y, z, and time. Things get a little bit more subtle when we're thinking about vectors in spherical coordinates or curvilinear coordinates, because we also have to think about the fact that like the direction of the radius at one point is not the same as the direction of the radius at the next point. So we not only have to differentiate the components and their dependence on space, but we have to also differentiate the basis vectors and their dependence on space. So one of the really nice things about the XYZ Cartesian framework is that it's parallel all the way out to infinity in every direction. So if I have k hat here at the origin, and j hat here at the origin, and I hat here at the origin, and then I go somewhere over here and evaluate k hat, j hat, and I hat, there's no difference. They don't vary from point to point. So I don't have to take the derivative of the basis vectors in addition to the derivatives of the coefficients of the basis vectors in Cartesian space, which makes things a little bit easier. In spherical space, you do, and that gets a little tricky with lots of examples in the book. Okay, what kind of derivatives do we want to take? Well, let's think. We had some operations last time. Oh, I just realized we forgot one. We could take a scalar and multiply it by a vector, and that takes a scalar and a vector, and it gives us a different vector. That's one. Or we could take a scalar times a scalar, and that gives us a scalar. Or a scalar plus a scalar, that also gives us a scalar. Or a vector plus a vector, that gives us a vector. Or a vector dot product a vector, that gives us a scalar. Those are the kinds of things we want to do because we want to preserve the symmetry of rotation and transformation of the coordinates that we talked about last time. And if we can write everything in terms of scalars, we know what's going to be invariant as we change our coordinate system. Or if we write things in terms of vectors and know that vectors have the specific property that whenever you dot them together like this, that's a scalar, a true scalar, then we know that that will be that the vectors have rotate and transform in the right way so that at least that part of their properties is conserved, is invariant to the transformation of the rotations. And so, what we'd really like to have is we'd like to have a way of differentiating scalars and vectors that gave us more scalars and vectors back. Okay, so I can take a time derivative of a scalar and I just get another scalar. The rate of time at a fixed point, the rate of change at a fixed point of a scalar with respect to time is just another scalar. Great. It's sometimes called the tendency of sitting still at the same point in space and just looking at the change in time of that. What if I take the x derivative? Is that thing gonna be a vector? Well, no, because it doesn't have enough components. One, the x derivative of a scalar is still just one thing. But is that thing a scalar? Well, no, it can't be a scalar because if I take the x derivative, that means I'm holding y and z fixed. But if I transform my coordinate system, turning x into y like we did before, the thing that corresponds to the x derivative in a different coordinate system is going to be corresponding to the y derivative in that system. So it's not a scalar. It's something funny else. What is a scalar? Well, there's this very convenient differential operator, del, which you can think of as being I hat partial derivative in x of just whatever's coming, plus j hat partial derivative with y of whatever's coming, plus k hat partial derivative of z of whatever's coming. And so this thing is a weird thing because these are operators that are going to operate on something else to the right, but I haven't told you what the thing to the right is yet. And it has I hat, j hat, and k hat, so it makes you think that it might be a vector because it's built out of vector components. And then it's got these funny derivatives, part on the x, part on the y, part on the z. This magical combination, if I take the gradient of a scalar, which is just putting in the x derivative, so putting in s here, so it's the x derivative of s in the I hat direction, the y derivative of s in the j hat direction, k derivative of s in the z derivative of s in the k direction, then this thing, gradient of the scalar, is actually a vector. And it does the transformations right. So the gradient of the scalar has a direction, which it inherits from these basis vectors. It has a magnitude, which I could imagine by taking the gradient of s, dotted into with the gradient of s, and that would be the magnitude of the gradient of s squared, and that's a real thing. Okay, that's a scalar. So it obeys the properties of vectors. It obeys, but it is a differential operation on a scalar. Well, what else could we do this thing? It sort of looks like a vector. Could we operate this del operator on a vector? Yes, we can. We could take del dotted into a vector. Be careful now. This one is I hat. So the I hat is telling us to take the ddx direction of only the first component of v. So we have ddx of v1 plus ddy of v2 plus dz of v3. We're summing them up because we've got a dot product over here. So this notation is driving us to consider this operation. The divergence of a vector is a scalar, just like the dot product of two vectors is a scalar. The divergence of a vector is a differential operator on the vector. Okay, cool. What about something that corresponds to the cross product? Well, there is something called the curl of a vector, which we can use the same trick before, where we were taking the determinant of a matrix, except now instead of the first vector, we write the partial derivatives on the second row, and then the elements of the vector, which if I could write, would be there. And so we get things like I hat times d by dy of v3 minus d by dz of v2 plus j hat plus k hat. And the j hat part is d by dz of v1 minus d by dx of v3. And the k hat part is d by dx of v2 minus d by dy of v1. And notice that the symmetry here is that if this part, the basis vector, is in the x direction, these don't have any x components or any x derivatives. They have the other two with a minus sign between them. This one's in the y direction. These don't have any y directions or any y derivatives. Okay, no y or y derivatives. And so the important thing here is that this takes a derivative operator on a vector and it gives you back a vector in return. So this one, and it has a kind of funny right-hand rule as well. If the vector, which we'll show in a second because I want to draw a picture of what the divergence looks like and I want to draw a picture of what the curl looks like. So let me erase and draw those pictures. Okay, so here's an example of a scalar field And this is just a 2D example because I can't draw a 3D scalar field easily without getting into colors and all kinds of things. But here's the topological map of a 2D scalar field. And here's where the scalar field is large, and here's where the scalar field is small. So what is the gradient of the scalar field? Well, the d by dx part of the scalar field is giving me, let's see, if we orient x and y like this. So first the scalar field is increasing as we go up with x. So d by dx is positive here. D by dy is negative here. D by dy is positive on this side. And then we are dropping back down. D by dx is now negative. D by dy is negative here. D by dy is positive here. So if I start drawing arrows that correspond to the directionality that I was just finding, you find that they are all perpendicular to the topo lines. Cool. And in fact, the magnitude is bigger where the topo lines are closer together because you're getting a larger change in s per unit distance. And so the gradient is the change in s per unit distance in an orientation towards the direction in which s is increasing the fastest. So all of these arrows are pointing from lower s on this outer topo contour to higher s on the inner, and they're pointing faster when the lines are closer together, which means your incline is steeper, getting to the higher s. So that's the way to understand the gradient of a scalar. What about the divergence of a vector? The divergence of a vector, this is a vector field, or a schematic of one, that has a lot of divergence in it. It's diverging. The vector lines are going away from some central portion, and they're going away faster the farther out you get. So if we think of this vector, which is pretty close to in the x direction from our previous coordinate system, which I should draw back again, then this component and the x component is getting bigger the farther we go towards x. It's getting smaller or negative the farther we go towards next. So when we think of this derivative, it's going from a negative value to a positive value. So it's positive when we think of this change in the divergence. It's all, and similarly, it's positive throughout this whole region in the middle where we're diverging away. The velocities are getting bigger the farther away from the origin point we're getting, and so we expect this to be a flow field with a lot of divergence in it. Okay, and this down here is a flow field that has a lot of curl in it. It's, if I'm thinking about the y component of my velocity changing with respect to x, so dv dx minus du dy, that being the critical component in this direction out of the board, it is a positive thing over here because the v direction is increasing with x, and here it's negative and becoming more positive, so it is also increasing with x here. Here, the u direction, and not using my same convention I just used, that should be u2, this should be u1, or this is the y component of u, this is the x component of u. Sometimes in fluid dynamics we write the y component as v, the x component as u, which is a little confusing from using v's the way we were using them before. But anyway, the x component here is increasing as we go up in y. It's becoming increasingly negative as we go up in y, and becoming decreasingly positive as we go up in y from the bottom. So on this part, but it has a minus sign, this is saying that this whole field has a positive curl. And so you can do a right-hand rule on that too. You let your fingers curl around in the sense of rotation of the flow, and the direction that your thumb is pointing is the direction of the positive curl. So just like the cross product brought us into a third dimension, the curl also brings us into a third dimension. Okay, so we have three derivative operators that can operate on fields that are scalars or vectors. that are worth thinking about right now. There are actually a few others, but they're pretty easily understood as the combination of these. So there's one particularly important one for us, the Laplacian, which is equal to the divergence of the gradient of a scalar. And so the Laplacian of the scalar is just two of these derivatives applied one on top of the other. The first one takes our scalar and makes it a vector, and then the second one brings us back to a scalar again, because this takes a vector and makes it into a scalar. Those are our derivative operators that are going to be the most important.